Welcome back. So today we're gonna talk about uh, another way to discuss the convergence or divergence of a series. Sometimes it's not that easy to really figure out what is the series convergent to. For example, if you look at the sequence of 1 over n squared, starting from 1 to infinity, or maybe I should write it this way, 1 to infinity, and then they ask you to find out the sum of this sequence, basically asking you what is the series corresponds to that 1 over n squared, n from 1 to infinity, which is 1 over 1 squared plus 1 over 2 squared, and so on. It turns out that the sum of this series is something like pi squared over 6, if I'm not mistaken, but calculating this is not that easy. So what we can say is, first let's figure out if this series is convergent or not, then based on that we can decide, okay, can we really find out what is the exact value of the series or not later on. So this section we're going to talk about integral test. It gives us an idea if a series is convergent or not, or divergent. So here let's look at the same example, 1 over k squared, k from 1 to infinity, which is the sum of these numbers, 1 over 1 squared, 1 over 2 squared. If you think about this, you can expect that this series is kind of convergent uh, based on the behavior of this summation. Numbers are getting smaller very fast, but we're not sure if that's the case or not. So what you do is think about each one of these numbers, 1 over 1 squared. If you look at the function 1 over x squared, corresponds to the 1 over k squared. If you look at this function, y equal to 1 over x squared, and let's say this is 1, 2, 3, and so on. If you remember to calculate the area under the curve, we would use the integration and say, okay, the area under this curve is the integral from, let's say, 0 to infinity, 1 over x squared dx. And if you wanted to approximate this area, we basically use rectangles to approximate each one. For example, at 1, we use the right endpoint and say, okay, this rectangle would have height 1, corresponding y value would be 1 over 1 squared. And the next rectangle, if we use the right endpoint, would have height 1 over 2 squared, and so on. This rectangle would have 1 over 3 squared. So these areas are kind of approximation of that integral, but it's an underestimate of the integral. So the integral is definitely larger than the sum of these smaller areas, because each area is an underestimate of the general total integral. So what we can say is basically this summation 1 over 1k is smaller than the integral from 0 to infinity 1 over x squared dx. But just to avoid the fact that we start from 0, let's make it to 1 and say, okay, if we calculate this area, then add up this small square, it's going to be exactly the same as, it's going to be still less than that approximation, so I'm going to write it as this way, 1 over 1 squared plus that integral. Just because I don't want to deal with 0 around 0, we have infinity as y value, so let's avoid that, meaning you approximate this sum, this area under the curve, plus this specific square. And that is still larger than this summation, because each of those squares would have exactly each one of these squares. So this square, for example, would have area of 1 over 1 squared. This area would be the height times the length. The length is 1, the height is 1 over 2 to the power 2. So that area would be, this is A2, if this is A2. This area would be exactly A1, that area would be A3. So if you add up all those areas, it's an underestimate of the integral of the 1 over x squared. So basically what can we say is, if this integral exists, then this summation must exist also because it's smaller than that. So I can say, okay, this is less than or equal to 1 plus 1 over 1 squared is simply 1. 1 from integral from 1 to infinity of 1 over x squared would be 1 over x, negative 1 over x, evaluated from 1 to infinity. And for that, we need to take a limit. So this would be 1 plus limit negative 1 over x, negative 1 over t approaching to infinity, minus replacing 1, which would give us negative 1 over. So basically, this is 0, and what you have is 2. So I can say this summation is definitely less than or equal to 2. What that tells us is that the sum of all these areas must be less than 2. So therefore, the series of 1 over k squared, 1 over n squared, or series of 1 over k squared, k from 1 to infinity, is less than or equal to 2, which means that series must be convergent. If you add up all those numbers, it's going to be convergent. Okay, so this integral kind of gives us an idea of how this series behaves. You don't need to always start from 1, you can start from 3. It doesn't really matter because the first couple of areas are finite numbers. So instead of starting from 1, I can start from 3. Doesn't matter. If it's still finite, then plus a couple of numbers of areas, then still you would have a finite number. That means the area of the squares would be finite, therefore the summation would be bounded. Okay, let's look at another example just to see. If you look at the summation of 1 over square root of k, k from 1 to infinity, and compare it to the integral, what we see is this curve basically is the curve of 1 over square root of x, and at each point, let's say this is 1, 2, 3, 4, and so on. At each point, if you look at the area, so here is the area of this square, the area of that square would be corresponding to the height times the length. The length is always 1, so this is always 1. So basically the area would be correspond to the height. And what is the height? 1 over square root of 1. What is the height here? 1 over square root of 2. And so on, 1 over square root of 3. So what would be the area of each one of these? It would be simply 1 over square root of 1, 1 over square root of 2, 1 over square root of 3, and so on. So if I add up all these areas, I'm overestimating. So if I add up all these, what am I doing is I'm overestimating the integral from 1 to infinity of 1 over square root of x, which means I'm saying that this summation is definitely greater than or equal to the integral from 1 to infinity of 1 over square root of x dx. Right, because the black curve is smaller than the sum of those squared. The area under the black curve, starting from 1, I should say from here, just to make it clear. The area under that curve is smaller than the sum of those squares, the area of those squares. So that tells us the sigma, the summation, is greater than the integral from 1 to infinity of 1 over square root of x dx. And if we calculate this integral, would be basically, you can calculate this would be 2 square root of x, and evaluate it from 1 to infinity, which means you can use limit 2 square root of t from 2 approaching to infinity, minus evaluated as 1, 2 square root of 1. So this is basically infinity minus 2, which is infinity. So what does it tell us? It tells us the summation of 1 over square root of k from 1 to infinity, has turned out to be greater than or equal to infinity, which tells you that this summation is never a finite number. So it tells you that the series must be convergent. So the series, must be divergent, not convergent. divergent. Okay, the difference between these two is one was underestimating, the other one was overestimating. But realistically, it doesn't really matter uh, if it's underestimate or overestimate, because you can always assume that, okay, instead of using this square to this rectangle to represent, I will use that rectangle to represent this rectangle to represent. So if one of these, uh, if this integral is divergent, then that tells you the series must be divergent. If the integral is convergent, that tells you that if the integral does exist, that tells you the series must be convergent. So these end up to be a representation of what our integral test is. So if you want to find out a series is convergent or divergent, assuming that you're dealing with a continuous function, f, where f is basically that corresponding to those AIs, ANs, and those AIs are positive, that means the area doesn't alternate, it's always uh, above the x-axis, and with the assumption that the function is decreasing. If it's not decreasing, then this overestimate and underestimate is not accurate. So assuming that the function is also decreasing over the interval from 1 to infinity, this realistically doesn't really matter to be from 1 to infinity, it could be from 3 to infinity, and so on, doesn't really make any difference. The first couple of terms are finite. So this part is uh, really not that important. You have to start with a constant up to infinity. Then what you can say is that the sigma of an is convergent if and only if the integral is convergent from 1 to infinity, or this it would be divergent if the summation is divergent. So if the integral is divergent. So basically this integral, if it is convergent, then the series must be convergent. If the integral is divergent, then the series is also divergent. So instead of convergent and divergent, maybe it's better to say if the integral exists, or if the integral is finite and the other one is infinite, then the series would be convergent or divergent. Okay. Sorry about that. My phone hurt. Okay, so let's do an example. So test these series for convergence or divergence. So our first example, let's try to see if we can figure out the behavior of this series. We're going to find out if this is convergent or divergent. We cannot calculate the exact value, but what we can do is basically figure out if this is going to be a constant at the end, if it's going to be a constant, or it's going to be infinity. So what I'm going to do is first I'm going to represent a function f of x, which is 1 over, instead of n, you would have x squared plus 1. If this is a continuous function over the interval 1 to infinity, yes it is. Is it a positive function? Yes, always it is. Is it decreasing? If you increase the denominator, then the function would decrease. So it's a decreasing function also. Then I can compare it and say, let's calculate the integral test from 1 to infinity, 1 over x squared plus 1 dx. Remember that those restrictions have to apply. Otherwise, you cannot use the integral test. So if I have this integral, if you remember, this is simply tan inverse of x evaluated from 1 to infinity, which is limit tan inverse of t approaching to infinity, minus tan inverse of 1. Tan inverse at infinity would be pi half, tan inverse of 1 would be pi over 4. And that turns out to be pi over 4. So what can I say? I can say that this integral must be convergent. The answer is not pi over 4. Do not write pi over 4. Pi over 4 is just tells you that approximately this integral, the result of this summation is close to pi over 4. It's not going to be exactly pi over 4, because this pi over 4 is either it's going to be an overestimate of this summation, or a close estimation of this summation. Let's look at the other example. Here's the other example, is summation. Change different color. So let's say we want to figure out what the summation of 1 over n minus 3 squared, n from 4 to infinity. We want to figure out if this is convergent or not. One thing that you notice, it doesn't start from n doesn't start from 1, and that is never an issue. If n starts from 4, that's still fine. If n starts from 10, that's still okay. Doesn't really always necessarily need to start from 1. That just tells you the first couple of terms, or we ignore those first couple of terms. So what I'm going to do is I'm going to think about this function 1 over x minus 3 squared. So is the function increasing or decreasing? Over what interval? Here's the good news. Since n starts from 4, I don't need to pick the interval to be 1 to infinity. I can pick the interval to be 4 to infinity. So this very first starting point tells you that. So in terms of starting from 1, you can start from 4. Even if this was like 2 or 3, doesn't really matter. In this case, 3 is not possible because you get 0. But you can always assume that this starts from some constant 5, 6, whatever, up to infinity. So I will look at the function in this interval and say, okay, the function is decreasing, since if you increase the denominator, the fraction will decrease. The function is always positive. So therefore, I can use the integral test. What is the integral test? The integral test would be the calculated integral from 4 to infinity of 1 over x minus 3 squared dx. And this is simply negative 1 over x minus 3. Yeah, you can use the substitution, evaluate it from 4 to infinity. And if you use, if you calculate this is limit negative 1 over x minus 3, t minus 3, t approaching to infinity, minus limit, minus negative 1 over 4 minus 3. So this is 0, approaching 0, since the denominator is approaching infinity, and you will end up with positive 1. So what can I say is, since the integral is convergent, so this must also be convergent. Again, the result is not 1, don't write 1, it only tells you that it's convergent or divergent. Okay, another example. This is kind of the one of the important examples actually, because we would use this later on. For what p-values this theory is convergent? Let me shift this up a bit. Okay. So the question is, for what p-value this theory is convergent, and we can say, let's think about first p negative. What happens if p is negative? If p is negative, what you have is simply the fraction would be something like 1 over n to the power negative 2. You can write that as n to the power positive 2. So if p is negative, then you can write it as something like n squared and n to the power some positive numbers. Some of those always would be, so it would be something like sum of n squared. And since that doesn't converge to 0, if you remember limit an and approaching to infinity must always approach 0, otherwise the theory would not be convergent. So in this case, if that's the case, then you wouldn't have this limit to be 0. So if p is negative, then limit an as n approaches to infinity doesn't equal to 0. So that means we're dealing with a divergent series. So where an is 1 over n to the power p. And also if p, then maybe I can say less than or equal to 0, because if it's 0, then you have a constant. What if p is less than, greater than 0? Then what happens? Then if p is greater than 0, what we have is, we have this function, the function 1 over x to the power p, to compare with. And over the interval 1 to infinity, this is a decreasing function, this is a positive function, so I can use the integral test to figure out what is the behavior of this function. So the integral from 1 to infinity of 1 over x to the power p dx would be subtract 1, add 1 to the exponent, subtract 1 from, so you can write this as integral 1 to infinity of x to the power negative p dx, and that would be x to the power negative p plus 1 divided by negative p plus 1, and this is where is it, from 1 to infinity, right? And the only issue is, let's assume that p is not 1. If p is 1, then we would have to deal with natural log. So for the moment, let's assume p is not 1. So what do we have? We would have the integral. This integral would be, let me rewrite it. It would be some constant 1 over 1 minus p times 1 over x to the power 1 minus p, evaluated from 1 to infinity. Okay. If this exponent is negative, what happens? If the exponent is negative, then when you calculate the limit at infinity, you will deal with 1 divided by x to some power negative, which would be x to that power positive. So if 1 minus p is negative, then basically what you have is 1 divided by 1 minus p times x to some power of a positive number, to some positive exponent. Because if it's negative in the denominator, you can move it in the numerator. From 1 to infinity, this would be approaching to infinity when you replace infinity. So in that case, we will deal with a divergent integral, which tells you it would be a divergent series. On the other side, if 1 minus p is positive, then what you have is 1 divided by 1 minus p as the coefficient times 1 over x to the power something positive here. Then evaluating from 1 to infinity, this would approach to 1 divided by 1 minus p. Because this term would be 0 when evaluated in infinity. And it would be 1 if you evaluated 1. And so when you subtract it from each other, sorry, this would be negative divided by that. So this would be the result, which basically in that case it would be convergent. And in the case if p is equal to 1, this is the simple sum of 1 over 1 plus, sorry, this is the same as sum of 1 over n. N from 1 to infinity, and we already know that this is a divergent series. So what we can say is basically, if I put all these together, I can say as a result, maybe note this, it's quite important, if p is less than or equal to 1, because if p is less than or equal to 1, then this term would be negative. That would be this case, and also this case. If that happens, we always have divergent series. If you look at this, they all were divergent series. So if p is less than or equal to 1, then the summation of 1 over n to the power p is divergent. And if p is greater than 1 strictly, then that series 1 over n to the power p is a convergent series. Okay, this is quite useful. We'll use this later on. Okay, so remember this. This is one of maybe the most important, not most one, but one of the important series that we would use for comparing other series. Okay, here let's do another example just to make sure. So if we're testing for convergence or divergence of a series, again, not finding the what is the sum? Basically, we're just trying to find out if the summation exists or not. What we can do is always try to find out if we can use the integral test. Not always possible. Ln x divided by x. If you look at this function, we would have always a positive function. The function would be decreasing, and as over the interval 1 to infinity. Sorry, I should mention this. And if we calculate, then now you can use the integral test and say, okay, what is the integral from 1 to infinity of ln x divided by x? Because it's quite difficult to figure out what is this summation really. You don't know what is ln2, ln3, those are decimal values. So if we calculate this integral, what you get is you have to use substitution. Let me do that. U equals ln x. And so one thing that you should check always, maybe before I mention this, you have to figure out if an is approaching 0 as n approaches to infinity. This is quite important. If that's not the case, you don't need to really go through this. So let me check that first. What is an? An is ln n divided by n. And if we calculate the limit, what is the limit? Ln n divided by n as n approaches to infinity. You can use the Hopital rule. Derivative of the numerator is 1 over n. Derivative of the denominator would be simply 1. As n approaches to infinity, this is going to be 0. So it tells you that this an is decreasing, approaching to 0. So now I can go on and try to use this function. Otherwise, it's not really necessary to deal with this with this integral test. It's important that you check this. And to see if it's increasing or decreasing, you can take a derivative of this function to see if it's negative over this interval or not. In this case, if you take a derivative, you'll notice that the function would be decreasing at some point. Okay, by the way, again, as I mentioned, this could start from 3. It doesn't really make any difference. As long as there is an interval like 5 to infinity, then you're still good to go to use the integral test. So 1 to infinity. And now if I calculate this using substitution, let me use substitution. U equals ln x. Du would be 1 over x dx. So what we have is the integral u times, instead of dx over x, I can write the from 1 to infinity. You can change that boundary, update the boundary, and calculate this. And this would be 1/2 u squared evaluated from 1 to infinity, and that is limit 1/2 u squared as u approaches to infinity minus 1/2 1 to the power of 8. That is simply infinity minus 1/2 infinity. Okay, so it tells us that this series is a divergent series. I can say divergent. Okay. Again, this part I didn't really mention it, but just to make sure that you guys know, the function that we picked, as ln x divided by x, call it y. This function, you should check to see if it's a decreasing function. If it's not a decreasing function, using the integral test is not quite an option. So if you take the derivative, y prime would be 1 over x times x minus 1 times ln x divided by x squared. This is simply 1 minus ln x divided by x squared. Okay, this function, if you want to find out if it's decreasing, y prime must be negative. If I let x to be 1, what do I have? I would have a positive value. I will have ln would be 0, so you would have y prime would be greater than 0, the derivative. So that means the function is already increasing at 1. But after you pick x to be greater than e, then y prime becomes negative because the numerator becomes negative. So this interval that I said from 1 to infinity could be changed to e to infinity. After that, the function is decreasing, and these lower bounds could be changed to e. E doesn't really make any difference. E squared, actually this one is not e, this one is maybe 1 simply, yeah, 1 squared. And you still end up subtracting a constant, that constant, whatever that constant is. Infinity minus a constant, still infinity. So it doesn't really matter where it starts as long as there is a point that the function after that would be decreasing. Okay, that is quite important check. But notice that the function after x is greater than e, then the function always be decreasing. This is quite important. Okay, so now if we use this idea, we can kind of approximate or estimate the remainder of a series or a tail of a series just by looking at the leftover. So let's say if we have a series an and from 1 to infinity, and we only add up the first 20, 30 terms of that series. What happens after that, the sum of those leftover 31, 32, 33 terms, or from an plus 1 up to infinity, some of these are called the tail of the series. So basically you have added the first 30, 40 terms of the series, and whatever is left over, it's quite small numbers. But you can kind of approximate what are those small numbers by using this integral. It's not going to be exact, but it's a good approximation because these squares turn out to be quite, this rectangle is quite close to the function. So the areas would be quite close to each other after a while. Maybe the beginning maybe there's a big gap and say, okay, these numbers are too different. That area doesn't really match this square. But after a while, these areas would be quite close to each other. And we can say, okay, the remainder of the difference of the total summation, this was the total sum, minus the first n-term summation, is basically the tail of the series. And this tail could be approximated by saying, okay, let's calculate this underestimate, and let's calculate the overestimate after a certain point. And what happens is the remainder is basically between these two. Okay, so the tail is this tail is less than this integral of the underestimate and greater than the overestimate integral. Okay, so basically I can say the integral of function f of x dx from n plus 1 to infinity is less than or equal to Rn, and Rn is less than or equal to the integral of from n to infinity. So that left point or right point is basically tells you the overestimate or underestimate. This one is an underestimate, and here was an overestimate. So the difference basically would be, this term would be less than the other. Okay. It's not necessary just to figure out what are these intervals, but it's a good idea that tells us how far we are from the remainder. Here's just an example to see. So let's say we approximate the sum of the series 1 over n cubed by using the sum of the first 10 terms. Then find out what is the estimate of the error. Okay, so if you add up the first 10 terms of that series, 1 over n cubed, n from 1 to infinity, we say this is almost the same as summation of 1 over n cubed, n from 1 to 10, plus some remainder. It's not exactly the same, but this remainder is what we're trying to approximate. So if we figure out the first 10 terms, add them up together, which means if I add 1 over 1 plus 1 over 2 cubed plus 1 over 3 cubed, up to 1 over 10 cubed. Since it's only 10 terms, I can use a calculator to calculate and find out what is the error approximation. and add that, I can say closely, not exactly, but the summation from 1 to infinity would be close to that approximation. So let me see if I can find out what is that summation. Let me use a calculator. 1 second, sorry. Okay, so that summation of the first 10 terms is basically here we go. It's this summation is something like 1.197. Okay, so I can say, okay, this sum of 1 over n cubed, it's close to 1.197 plus some remainder. And what is this remainder? This remainder is basically the tail of that series. And how do we find that remainder? We can calculate the integral. Say, what was the integral? The integral is the function was 1 over x cubed, and we just need to figure out what is the integral from 10 to infinity of 1 over x cubed dx. That would be kind of an approximation for the tail of the integral. Okay, so normally, since we don't know what is this 10, or we assume that we stop at an. So let's not do 10, let's take it n, just to say, okay, this is either an overestimate or underestimate by picking n to be 11 or 10. So here, let's calculate this integral. This integral would be simply integral x to negative 3 dx from n to infinity, and this is x to negative 2 divided by negative 2 evaluated from the n to infinity. And if you look at this, this becomes negative 1 over 2x squared from n to infinity. Maybe this is easier to see, and if you replace infinity, you will get 0 by taking the limit. So basically, this becomes 1 over 2n squared. So the remainder that we have, this remainder is kind of close. Okay, so I can say the remainder is kind of bounded between 1 over 2 times n squared, and the other side would be 1 over 2 times n plus 1 squared, where in this case n is simply 10, because we stopped at 10 terms. So I can say, okay, this remainder of this series is bounded between 1 over 200, and here is 1 over 121 times 2 is 240. Okay, so I can kind of approximate and say, okay, this is close to 1.197 plus something like 1 divided by 200. Because this is if I pick 10. If I pick 11, I can say 1 over 242. Generally, I think overestimate is a better idea, picking 200. So in this case, that would be an approximation of the result. Okay, so the error is bounded by that much. Error is bounded by 1 over 200, or you can use 1 over 200. So the interval that you represent, plus this r, let me keep it this way. So the interval that you represent basically tells you where the error lays in. The error of the estimation lays in between these two numbers, which is kind of close. I think this is like 0.005, and on the other side you would have something like 0.004 or something. Yeah, so the error is quite small. Okay, there was a part B to this question. How many terms are required to ensure that the sum of the sum is accurate within this range, within the range of 0.0005? So that tells you where do you have the tail, which is the remainder, where do you have the remainder to be less than or equal to 0.0005? And since we figure out what is the remainder close to, the remainder is less than 1 over 2n squared. I can say let 1 over 2n squared be less than or equal to 0.0005, and you can say n 2n squared, let me do this, 2n squared must be greater than or equal to 1 divided by 0.0005. And this is just a simple fraction that would be 200, and n squared must be greater than or equal to 1000, and therefore n, if you do this division, you'll get 1000. So this would be n must be greater than square root of 1000. And this is close to 32, I think 31.2 or something. So I can say n must be at least 32. Okay, if we do 32 terms, add up 32 terms together, the remainder would be less than 0.005 as the error. Okay, so this estimation is kind of useful to approximate, okay, what is the leftover basically. They can give you an overestimate and underestimate of the range. Okay, so this is it for this section. I will stop here and we will continue next time, talk about comparison tests and another method to discuss the convergent or divergent of a series. So let's stop here.